Hi guys, welcome to Mrs. Stracuzzi's gravity tutorial. I'm going to talk about the lab that we did yesterday quite a bit. So if you weren't here for this lab that involves this image that you see on the screen, then you should go back to the Google Classroom and find this lab simulation and do it so that you have some idea what I'm talking about before you watch this tutorial. For those of you who did do the lab together yesterday, I have a few things I want to point out to you. There were two things that you could control in this simulation. You could change the mass of the two spheres, M1 and M2 they were called, and they're called that because they're masses. So mass 1 you could change the sphere by moving this slider, and mass 2 you could move this slider. So I've set it up so that mass 1 has a mass of 50 kilograms and mass 2 is 200 kilograms. And then I put them so that they're 4 feet apart. This one's on the 3, and this one is on the 7. This is a meter stick, I'm assuming this is a meter stick. Actually, it's not a meter stick, but a 10-meter stick, which would be a really long meter stick. But gravity is what we're actually measuring here, and gravity is a force. So if you look up here, the force that is acting on each of these spheres because of gravity, each of those forces is identical to the other one. Look, the force on this ball from this ball is equal to this amount, which is a really small number of newtons. A newton is a unit of force. It's kind of like our word pound. So you could say that that many newtons is like a feather's worth of force resting on you. It's nothing. This should make perfect sense to you because think about it. We've got two objects. One of them, it has a mass of about 50 kilograms. That's about the weight that most of you are. And the other one has a mass of 200 kilograms, so that's like 4 of you standing in one place. And imagine that you and your group of friends are standing 4 meters apart. So that would be like, less than half the length of the room apart. Do the two of you feel any attraction due to gravity? No, probably not. You don't feel yourself rolling into them or being pulled towards them, and they don't feel themselves being pulled towards you. Technically, you are, though. It's just an itty-bitty tiny amount of force, that much. Notice that the force on the red sphere is the same as the force on the blue sphere. Both of these objects are pulling each other with an equal amount of force. That's going to be really important later on. The point of the lab was to show you Newton's law of gravity, which is over here on the left-hand side. And I'm going to reveal some words. That's why there's all this space there. So I'm going to show you what Newton's law of gravity says in words. But the picture down there on the bottom left is a picture of the equation that Newton came up with that describes the relationship between two objects that are attracted to each other by gravity. So go through the picture with me and see if you can figure out what everything is. So you've got mass 1, which is this blue sphere, which is attracted to mass 2, which is a green sphere. And you have r, which stands for radius, but it's really just the distance from the middle of sphere 1 to the middle of sphere 2. Then you have the force of attraction from the blue ball to the green ball and from the green ball to the blue ball. And basically, this all comes down to the force is equal. Force 1 is equal to force 2, and both of them are equal to this mishmash of letters. That capital G stands for the gravitational constant. And I know what you're thinking. You're thinking, hey, isn't that 9.8? Nope, that's a different constant. That's the acceleration due to gravity. I know, very confusing. The gravitational constant is a tiny itty-bitty number. We'll talk about it in a minute. It's kind of like the number pi, right? Pi is a number that comes up in equations all the time. It's equal to something like 3.14, a whole bunch of decimals forever and ever and ever. Capital G, the gravitational constant, also is a number. It's just incredibly tiny. So if you take that incredibly tiny number, this G, and you multiply it by the masses multiplied times each other and then divided by the radius, the distance between them, that's this thing here. If you do all that, you can figure out what the force is of gravity between the two objects. It's kind of amazing that Newton was able to figure out this equation without all the modern equipment that we have, but somehow he figured it out. And I think he basically did it by examining the tides, but that's a whole nother long story that we can't really get into here. So in words, not in equation form, but in word form, what does Newton's law of gravity say? Well, the first thing it says is every particle in the universe attracts every other particle in the universe. We're using the word particle here. We could also say every mass in the universe attracts every other mass in the universe. Or we could say thing. Everything in the universe attracts every other thing in the universe. That would just be not very scientific-y sounding. Or we could get really goofy and just say every thingy in the universe attracts every other thingy in the universe, which would be plain silly. So this is just the fact that everything has gravity. Every single piece of matter in the universe attracts every other single piece of matter in the universe. So far, so good. Then from the lab simulation and from Newton's own observations, we know that the force of attraction between these particles increases as the mass of the particles increases. So if either of the masses, mass 1 or mass 2, gets bigger in terms of mass, then the whole equation gets bigger, so the gravitational force increases. And then finally, the force decreases as the distance between the masses increases, or the particles increases. So if I slide M1 and M2 apart, if I make this one go, whoa, 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 I hate when that happens. When I make this one go this way and this one go that way, then the attraction between them will decrease. So every particle in the universe attracts every other particle in the universe. The force increases if the mass increases, and the force decreases if the distance increases. These statements are given to you on the note sheet. So that's already written in for you. You don't have to copy it down. And this equation is sitting there too. It's in a slightly different form. It doesn't have F1 equals F2. It just has F equals, or Fg equals, for the force of gravity. So this is a law. Laws describe nature. They tell us what we see. They say, these are the observations. We've observed all of these things. So Newton observed these things, but he could not explain them. That took a genius called Einstein to do that. Einstein came up with a theory of gravity. Theories explain observations, which is harder to do. This is similar to what we had to do with our black box. If we made a law of the black box that we examined at the beginning of the year, the law would say something like, if you pour this much water in, and it's turned to the left, it comes out red. If you pour this much water in and it's turned to the right, it comes out purple. Those would be observations. Then our theories of why the box did that would be our drawings that we made, our models. Einstein has a model that he uses to explain gravity, and it's pretty cool. First thing you gotta realize is that Einstein comes up with a theory because Newton's law did not explain the origin of gravity. It also doesn't explain why gravity does what it does. So a theory was needed to try and explain it. Now, don't worry about this because I'm not going to hold you to this, but Einstein actually would have said that gravity isn't a force at all. He would have said gravity is an effect. It's an effect of space itself. He said space is causing gravity. And by space, I don't mean like outer space, that's part of space, but there's also plenty of space between you and other objects. Even if there's air between you and the other objects, a lot of the air, there's spaces between the particles of air. So there's a plenty of empty space in the universe, and that includes space right in front of your face. Einstein's idea was that a mass changes the space around it. If you put a mass in space, it curves the space, and it makes a dent in it. Periods 3, 4, and 7, I demonstrated this using a garbage can, basically, with something springy drawn over the top of it, and I will show you videos of that in a second. Period 2 didn't get to see that, so this is going to be totally new to you. But Newton was trying to explain these three observations. Why are particles attracted to each other in space? Einstein's theory is going to try to explain that. Why does it happen that the more mass you have, the more gravity you have? Einstein tried to explain that with this model. And why is it that the further apart the objects get, the less gravity there is? Einstein tried to explain that too. So let's look at the videos of my demonstration to see what he's talking about. Actually, I lied. First, let's fill in that note sheet. The first thing on that note sheet that you actually have to fill in is you have to convert the gravitational constant, which is 6.7 times 10 to the negative 11 up top, into standard notation or standard form, which just means that you'd have to do this. You have to put a decimal down, right? Because a negative exponent means that this is a small number. And negative 11 means that we have 11 spaces before we get to the number. So before we get to that decimal point, rather. So you need to move your decimal so that you have a total of 11 spaces before you get to the 6 and the 7. So you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the 6, and 11 is the 7. That is that number written out in standard notation. It's really, really small, right? I apologize for my sloppy looking 0 there. So that is G. G is the gravitational constant. That's that really, really tiny number that is in that equation that we talked about before. The next thing that you're going to have to do is fill in how Newton's laws are related to gravity. So we'll come back to this page after we look at some of the videos that I made. Okay, so I'm going to take you through Einstein's explanation of why gravity happens. His idea was that space is actually a fabric, that there's actually something there that we can't detect. So what feels like emptiness to us actually has a kind of substance to it. And he would draw that substance as a three-dimensional grid, basically a block or a cube that has grid lines on it. His idea was that space, if there was no mass in the universe, if there were no objects, no particles, no planets, no you, no dust, nothing, space would look like that block. The entire universe would be broken up into equal little boxes like that of space. However, the universe has mass in it. So whenever you take some mass and you put it into a piece of space, you get this totally warped looking cube. What's happening here is that chunk, that purple chunk of matter in the middle, actually bends space around it in all directions so that all of those grid lines get distorted. So space becomes curved. And he actually thought space and time were linked together. So he would have said that this is the space-time continuum being curved by matter being placed in it. His idea was that any object that we place in space will cause this bending or warping of the space-time continuum. However, most of the time it's not very noticeable. So the amount of warping that, say, you do in space is not much. The amount of warping the Earth does, however, is quite significant. And that's because Earth has a lot of mass. And mass is really a measure of the amount of matter you have. So the amount of matter really matters. The more of it you have, the more curved space becomes around that matter. So this is three-dimensional, but it's really hard to make a model of that you guys can like touch and feel and see and understand. So in periods 3, 4, and 7, I actually broke out my garbage can model of gravity. So this is just my big garbage can with a piece of fabric stretched over the top to make a gravity well simulator. A gravity well is just one part of this picture up here. It's the very tippy top part. So it's one slice of space that has been curved by a mass. And I have some heavy objects in the middle here. Those are actually those squares that I have that are really heavy that have the hooks on them. And I put those in the middle, and that creates a dent in the fabric, just like putting this object in the middle here creates a dent in space. And then you can kind of see what this curve causes to happen. So I'm going to play this video down here in the bottom and show you some of the experimentation that I did with this in some of my classes. This is especially for period 2 or anybody who is absent, because I did this little demonstration, like I said, for periods 3, 4, and 7 yesterday. So you can kind of watch it. I'll talk you through what I'm doing in each one of these demos. Okay, so I made it nice and big for you. Before I hit play, on top of the garbage can, I have a much smaller version of the same thing. And you can see all the pretty colors. That's because instead of using a piece of black fabric, I got this book sock from Allie. She's in my period 2 class. So this is why I didn't do it in period 2. I was busy setting it up. So it's the same exact demonstration. You're going to see it on both with the smaller one and with the bigger one. The reason I wanted to do it on the small one for you is because the book sock is much springier, so it responds better than the material I have going across the garbage can, which is a little bit tight. So you can kind of see, I'm going to play the video and there's no sound. Well, now there's no sound. And I'm just going to talk you through all the little demonstrations that I'm doing with gravity. So the first thing that I did is I just put one of those heavy masses in there, and you can see the dent that that makes in space. And as I add more of these heavy masses, you can see the dent getting deeper and deeper. And this is important because Einstein is trying to explain an observation about gravity. Remember, Newton said that the more mass there is, the greater the pull of gravity is. Well, Einstein would say that the reason for that is because the dent in space gets deeper and deeper the more mass you have. And that dent, you'll see in a second, is really what we think of as the force of gravity. So I'm going to take a marble and I'm going to let it put it at the edge of this gravity well, and you can see it rolls right down, which is what objects do around the Earth, for example. And if you give that marble a little bit of forward motion, it'll orbit for you, just like our moon does around us. Or so the moon is like a low gravity environment, but actually zero gravity doesn't exist. When people are floating in spaceships that are between here and other planets, they're doing that mostly because they are in free fall. So as they fall towards the Earth, they're usually in orbit and they're falling towards the Earth. If that's the spaceship and they're inside of it, the spaceship and the person are both falling at the same rate, and so it feels like they're weightless. Basically, that's because there's no normal force. We can talk more about that. All right, let's go back to those Newton's laws. Remember my ugly zero? There it is again. So what about Newton's laws and gravity? Well, I bring this up because Newton's first law, it doesn't have a lot to do with this, except that it's important to realize that Newton's first law is the law of inertia, right? So according to the law of inertia, an object in motion stays in motion until something makes it stop, and something that's stopped stays stopped until you make it move. And inertia is really your resistance to changes in motion. So we would say that the inertia of the Earth is way greater than your inertia. And that's really important when you think about gravity, because it's much harder to move the Earth than it is to move you. This also relates to Newton's second law, F equals ma. So you need more force to move something with more mass. So the Earth has more mass than you do, so it takes more force to accelerate it. This explains why the marble falls towards the Earth, but the Earth doesn't seem to fall towards the marble. We did this in class when we did the lab, that analysis question that had all that math in it. That analysis question basically was pointing out to you that the Earth accelerates a tiny amount compared to you. If you do the math right, you notice that you accelerate at 9.8 meters per second squared. That's the acceleration due to gravity near Earth. And the Earth is accelerating at a ridiculously tiny number. It was like 0.00000, and it went out for like forever before it came to an actual number. So basically the Earth barely moves as a result of you pulling on it. Newton's third law applies because gravity is an action-reaction pair. Because all forces are action-reaction forces. So gravity is an action-reaction pair. What that means is the force on you is equal to the force on the planet Earth. Both you and the Earth pull on each other with the same amount of force, but in opposite directions. Okay, this tutorial is pretty long, but you did have a whole class period to watch it. When you're done, if you want to try to do your archive, your full archive, that's what I would recommend doing. You could certainly refer to this tutorial while you do that, and you can use pictures from here for your artifact. A lot of you forget all the time that you have to include some kind of image in your archive in order to get full credit. I did say on the classroom that I was going to post a rubric, so I will post the archive rubric for you as well, just in case you've lost it or lost track of it, so that you can remember how I'm going to grade you. All right, guys, hopefully I will see you in class tomorrow. Take care.